evening. Welcome to tutorial session 11. So I'll just wait for 1 more minute so that other students can join. Then I'll start the tutorial. Okay. Meanwhile, I will discuss what has been covered in this week 11. So in the previous week, we were looking for the Nyquist plot. How to draw the Nyquist plot as omega is varied from 0 to infinity. Okay. So we are mapping the points from S plane to GS plane. Okay, that is called Nyquist plot. So we have drawn, we have plotted the Nyquist plot from 0 omega equal to 0 to infinity. But if you can see how to plot from for the negative frequencies, it is a mirror image of that. So you can see from here. Okay, in this graph you can see. So the Nyquist plot for the positive frequency is the negative j omega axis. Correspondingly, for the negative frequencies, you can see the Nyquist plot is plus j omega axis. Okay, because this is very critical when we are going into the stability analysis using the Nyquist plot. Okay. So week 11, so we have seen the Nyquist plot. Now we'll see how to use that uh, to uh, to see the stability of the system, right? So we have seen so what we want to do, stability means we want to see the closed loop poles. So we want the closed loop poles to be lying in the left half plane. Okay. So when these poles are lying in the left half plane, we'll say the system is stable. Okay, that's what we want. But here what we want to do is we want to observe the stability by seeing the open loop transfer function. So what is open loop transfer function? Open loop transfer function is G into H. Okay, so basically we are looking for the poles. So poles are the roots of characteristic equation. So this is the characteristic equation, right? 1 plus GS HS, and the roots of this equation are the poles of the closed loop transfer function. Okay, so here GS HS is the open loop transfer function. So here it's been denoted in the form of numerator divided by denominator. Okay, so here we are concerned about 1 plus GS. So you can see what are the numerator and the denominator. So in this case, zeros of 1 plus GS HS is the closed loop poles, right? And the poles of 1 plus GS HS is the open loop poles. So we'll be using this critical information in the while we are drawing the Nyquist plot. Okay. So for that we have seen the mapping theorem, right? So what we are doing here, we are mapping the closed contour in S plane to f of S plane. Okay, so we have the complex valued function f of S. So what we are doing, we are taking a closed contour in the S plane. So it is closed contour. So you can see we are in this case green and the black one. So that is the closed contour, and correspondingly we are mapping each point in this contour in the f of S plane. Okay, so just put different values of S and you will get f of S, right? So f of S, if you take the closed contour, then in f of S plane also you will see the closed contour. Okay, so these two contours are not same, but it's a very important thing. What we can see is this. Okay, so if we take a contour in S plane which has Z zeros and p poles. Okay, so you have to take the contour such that the poles and zeros does not lie on the contour. They can be outside and they can be inside. Okay, but they should not lie on the contour. So here Z is what? Z is the number of zeros of Fs within the closed contour. That's what I have said. And P is the number of poles of Fs within the closed contour. Okay, so NC is the number of clockwise encirclement of the origin in the F of S plane. Okay, so if you see the black contour here, okay, this one, so you can see it has Z one pole, two pole and one zero. So correspondingly, NC is equal to 1 minus 2. 1 minus 2 means NC is equal to minus 1. So NC is so we are taking NC as number of clockwise encirclement. Since it's NC is equal to minus 1, that's why the encirclement will be anti-clockwise. So you can see here. Okay. So this information we'll be using, and this is how we'll be using. So the contour in our case in S plane, we'll be taking the entire right half plane. Okay. So from minus, if you see the j omega axis from minus infinity to infinity, and it will be a semicircle of infinite radius. Okay, this is the contour we'll be taking. Okay, and since what we want here is we want for the closed loop stability, so number of poles lying in this portion should be 0. Okay, that means if you see NC equal to Z minus P, what we want is Z equal to 0, right? Because Z is what? Z is, if you see here, zeros of 1 plus GS HS is closed loop poles, right? So in this contour, we are looking for zeros, but actually what they are the closed loop poles. So that's why we want Z to be equal to 0. That's why we are taking the right half plane. Okay, so similar things. So in the first case, what we have taken is we have some assumptions initially that none of the open loop poles and open loop zeros lie on the j omega axis. Okay, so for the exceptions also we have taken into account what we do. Okay, so and also in this case we are assuming the open loop transfer function to be a proper transfer function. Okay, so if it is a proper transfer function, that means what? So n is n is number of poles and m is number of zeros of open loop transfer function. Okay, so if you do this, so what you will get this. Okay, so if you put the limits, that will be either 0 or a non-zero constant. Okay, so when we are putting the limits of S tending to 0 GSHS, what does it means? We are accounting for this region. Okay, this region. Okay, so this is in S plane, and if you go into f of S plane, this entire infinite semicircle region will correspond to a single point. Okay, and that single point can be a 0 or some non-zero constant. Okay, okay, so what we have, see, for closed loop stability, NC should be equal to minus P, because Z is equal to 0. Z is what? Number of closed loop poles. Okay, and number of closed loop poles lying in the right half plane. And what you want for the stability, that and the number should be equal to 0, right? So this is okay. Now NC should be equal to minus P. Minus means anti-clockwise direction. So the contour in 1 plus GSHS plane should encircle the origin P times in counterclockwise direction. Okay, so you can see here 1 plus GS is equal to, so f of S. So what is f of S function? 1 plus GS HS. But what we are looking for is GS HS. GS HS is the open loop transfer function. Okay. So what we do, we just subtract minus 1 from this contour. So what now the new thing what we will do is we will now see the encirclement of the minus 1 point. Okay, so this is a slight adjustment. So you can see here. Okay, let me take the highlighter here. Okay, so in this case, what we want is we want to vary S from minus infinity to infinity. Okay, already you're seeing in the Nyquist plot, as omega is varied from 0 to infinity, we can plot the Nyquist plot, right? So here omega is varied from minus infinity to infinity, and for the semicircle already you know from here, for the semicircle that will be a 0 or non-zero constant. Okay, so we'll be plotting this plot. So already we have seen for the 0 to for the positive frequencies, but in this case we'll be also seeing for the negative frequencies. Okay, So not negative frequency, omega is a variable, just minus infinity to 0 minus. Okay. And what we have seen in the previous week. Okay. So this one. Okay. This is the Nyquist plot for both the from minus infinity to infinity. Okay. And for the negative omega, what you do is just the mirror image of positive omega. Okay. That's how we'll draw the Nyquist plot for the negative frequencies. Okay, so what we do if we have some poles or zeros on the j omega axis or the origin, okay, so we just take d2, okay, a small semicircle. So you can see here, very small semicircle we do, and we'll just cross that. Okay, we'll not include in the contour. So for that, if you see, we'll take the value like this. S is equal to some eta value e raised per j theta. It's a small semicircle we are taking, and so s is going from 0 minus to 0 plus, and theta you can see from minus 90 to 90. So correspondingly, what we'll do, we'll just put the values in j of h of g into h. Okay, and we'll get the values here. So you can see on almost all the time you'll get this, because we have the proper transfer function, right? Magnitude will be high, high means infinity, okay, and phase we'll see, it depends on the open loop transfer function. Okay, so this was the particular example they have taken, and we have seen the concept of relative stability. So earlier when we talked about stability, we were talking about the absolute stability. What does absolute stability tell us? It tells us that when a system is stable, that means its closed loop poles are lying in the left half plane. Okay, then we say the system is absolute stability. Okay, but here you can see relative stability. What does it means? Okay, so we are just comparing two systems here. So you can see the red system 1, so it's less stable as compared to stable 2. So you can see, so since we are doing the modeling, right, a lot of things can happen, go wrong in the modeling. So we can see a pole is not fixed. Okay, so you can see the pink circle. So the pole can lie anywhere inside that circle. Okay, because of parametric uncertainties, unmodeled dynamics, or modeling errors. Okay, there can be various reasons for that. So that's why we have term relative stability. Okay, so relative stability means system 2 is more stable as compared to system 1. Okay, so how to define, like in terms of some variables. Okay, so how to quantify this relative stability. Okay, so we have defined. So what we do, we know uh, when the system becomes unstable. Okay, when its closed loop poles are lying in the right half plane. Okay, so it has to cross the j omega axis. Okay, so it has to cross from j omega axis to the right half plane. Okay, so that's what we are taking here. Okay, so you can see here the closed loop system would become unstable when its poles cross the j omega axis. Okay, so under this scenario, what will happen? So we will get this. Okay, g of j omega, h of j omega. That is what this is called. This is called sinusoidal. If you put s equal to j omega, it's called sinusoidal transfer function, right? So that should be equal to -1. So -1 means magnitude is equal to 1 and phase is equal to minus 180 degrees. So if you see what is in terms of Nyquist plot, so the closeness of open loop transfer function, the sinusoidal transfer function to -1 point in G of HS plane indicate a relative stability. Okay, so few terms here, gain crossover frequency. So this is the frequency when the magnitude becomes 1. Okay, so at what frequency the magnitude becomes 1, and again other term is phase crossover frequency. So at what frequency the phase of the transfer function is equal to -180 degree. Okay, so we have seen with the example. Okay, and similarly, so we have seen with respect to the Nyquist plot here. Okay, correspondingly what, so now definitions, phase margin and the gain margin. Okay, so what is gain margin? It is the reciprocal of the magnitude of open loop sinusoidal transfer function, right? This is the magnitude here, you can see. So reciprocal of it. So you can see why that reciprocal, okay? Because you can see here, so if I zoom this, so this point, if you see this point is like, though its phase is equal to minus 180 degree, but its magnitude is less than 1, okay? So what should we multiply so that its magnitude become 1? So if its magnitude become 1 and the phase is equal to minus 180 degree, then we'll say, okay, so what will happen then? This condition is satisfied. 1 plus GSHS equal to 0. Okay, that's what we want, right? So this is the gain. Okay, so this is the gain. So that's why. So the definition of gain margin is reciprocal of the magnitude. Okay. So similarly for the phase margin, it is the additional amount of phase lag that needs to be added to the system. Okay. So we have seen for that also. So if I this point, right, this is the phase, and you can see what should be the angle that should be added so that the system becomes unstable. Okay, so the definition should be clear. So this is phase margin, 180 plus phase of that at gain crossover frequency. Okay, so we have seen for the Nyquist plot. So but these definitions also apply for the Bode plot, because you'll see mostly in practical systems what we see is will be we are very comfortable with the Bode plot, right? And just by seeing the Bode plot, you can visualize what is the phase margin and the gain margin. So you can see here, okay? So the phase margin is calculated at gain crossover frequency. Okay, so you can see here at gain crossover frequency, the magnitude is equal to 0, right? That means equal to 1. So this magnitude is shown in dB. That means in absolute terms, it's equal to 1. Okay, so we calculate the phase margin. So this is the phase margin. In this case, it's positive. That means we have this much amount of particular amount of phase margin. Okay, so that means still system is stable. Okay, correspondingly at phase crossover frequency, we calculate the gain margin. Okay, phase what is the phase crossover frequency? It is the frequency at which the magnitude of the phase of the transfer function is minus 180 degree. Okay, and correspondingly you calculate the gain margin here. So in this case, it's minus 20 log of magnitude. So minus 20, right? So in this case, it's 20 log of the magnitude is minus, so minus of minus becomes plus. So here that's why it's written positive gain margin. Okay. So two more important terms they have discussed here. So one is cutoff frequency. Okay, so cutoff frequency is a frequency at which the magnitude of the closed loop frequency response is 3 dB below its low frequency value. Okay, so this is the definition why we take this 3 dB. It is related to the power. Okay, so you search on the net how it is related to the power. Okay, because your magnitude becomes 1 by root 2, that's fine, but your power becomes half of the input power at this point. Okay, once you go 3 dB below the low frequency asymptote value. Okay, and other definition, so the frequency range from 0 to omega c is called the bandwidth of the system. Okay, and the cutoff rate, it is the slope of the log magnitude curve at the cutoff frequency. So we are talking about what is the slope of this. Okay, after the cutoff frequency. Okay, it is the slope of the log magnitude curve at the cutoff frequency. Okay, so so one more thing we have studied is why pole pole zero cancellation is not allowed in the right half plane. Okay, because we don't know exactly where the pole is lying, right? It's, if you look at this picture, okay, you see at this limit, we actually don't know. We are just showing, okay, the poles are lying on the left half plane, but they might be lying anywhere inside the circle on the circle, right? So that's why we cannot know the exact location of pole for a system. So that's why we cannot cancel it really. So that's why we don't do the pole zero cancellation in the right half plane. Okay, that's why we have the closed so much of these things, controller design and all these things. Okay, so this was covered up to in this week. So let me ask you, do you have any doubt? Then we'll go to the assignments for the this week. So any doubt? Okay, we'll start with the tutorial questions. Okay, so in this so in this case, first few questions are very simple. Okay, so I want you to answer. I want the solution from you. Okay, so first question is, consider a unity negative feedback closed loop system whose open loop transfer function is this. Okay, the open loop poles are. So can you find out open loop transfer function for the unity negative feedback is given? So very simple, like, okay. So you want to find the open loop poles. What you do, see the denominator. Okay, you need to find the roots of this. Okay, and the roots of the denominator are the open loop poles. Okay, so what I can write here. Okay, so I have done steps so that you can understand what are the factors for this equation. Okay, two roots I'm getting. So s equal to 1 and s equal to -8. So in this case, I hope everything is correct for this. Yes. So these are the two roots, right? S1 and S2. And these two roots are the poles of the open loop transfer function. Very simple. 1 and -8. Okay. So what you can see, one root is lying. So one pole is lying in the right half plane. Okay. But this is open loop transfer function, right? You can stabilize it. No problem. Closed loop pole should not lie on the right half plane. Okay. So S equal to 1. Okay. So any doubt? I don't think so. You should have any doubt in this case. Okay. I'll go to the next. In problem 1, the closed loop poles are. Okay. So I quickly do this. It's very simple. Is square. So closed loop transfer function. How to find out? This is open loop transfer function. Okay. So which is okay. So this is the closed loop transfer function, right? But what we want is closed loop poles. So how to get the closed loop poles? So this is the characteristic equation, right? The roots of characteristic equation are the closed loop poles. Okay, so directly I'm writing it. So we have to find the root of this equation. Okay, so s square, this is 9s plus 6, how much? 8. Okay, so what you'll get s plus 1 and s plus 8 equal to 0. Okay, So for the equation, you have two roots which are s1 is equal to -1 and s2 is equal to -8. Okay, you can see they are lying in the left half plane. Okay, so what can we say about the system? The closed loop system is stable. Okay, so -1 and -8. Okay, any doubt in this case? Very simple. Closed loop transfer function. So find the roots of 1 plus GS HS or the characteristic equation. Okay, very simple. So okay, this is from problem 1 and 2. One can conclude that the mapped contour of the Nyquist contour in GSHS plane, okay, where GSHS is the open loop transfer function in circle. So now we have to find out the we have to comment, right? So in GSHS plane, what is happening? So how many encirclement we have to find out? Okay, so what we have seen. So GSHS is S plus 8. Sorry, this is S plus 2. So let me write. Okay, and what we had written two factors, right? S -1 and S plus 8. Okay, so what we can see here, so you see how because in case of stability, what we used to see, NC is equal to Z minus P, right? And what is Z? So this is closed loop poles, sorry, yes, poles, and this was open loop poles, right? This you have to find out. And in the question, what is asked is this NC, okay? Because we have the information about Z and P, right? Because we have calculated poles for the open loop as well as closed loop transfer function. Very simple. Okay, so okay, let me also write the roots. So this we want to find out, and for the closed loop transfer function, okay, so it was GS. This is the transfer function. So what important thing is, we from the open loop transfer function, what is the value of P? P is open loop poles. Okay, so open loop poles lying in right half plane. Okay, and Z is closed loop pole lying in right half plane. So what can you say about P looking at the open loop transfer function? So how many poles are lying in the right half plane for open loop transfer function? Can you answer this? So in the question, it's NC value is asked, right? How many encirclements? And we have the information for Z as well as P. Okay, so P is open loop poles lying in right half plane. Okay, so if you see the open loop transfer function and if you see the denominator, right? These are the poles of open loop transfer function. Okay, and how many poles are lying in the right half plane? You can see one pole, right? S equal to 1. Only one pole is lying in the RHP because S equal to -8 is lying in the left half plane, right? Okay, P is equal to 1. Let's find out what is the value of Z. Okay, so Z, let me write the 1 plus GS HS. So I'm just writing 1 plus GS HS equal to 0. Okay, so which was, okay, now you tell me what is Z. So it is closed loop poles lying in right half plane. So how many poles are lying in right half plane? Just look at this. Okay, roots of this equation are closed loop poles, and you can see S1 and S2 both are negative, right? So both are negative, that means they're lying in the left half plane. So Z is equal to 0, right? So no closed loop pole is lying in RHP. Okay, so what is NC then? 0 minus 1, right? So NC is equal to minus 1. So plus is clockwise encirclement and minus 1 is anti-clock encirclement. Okay, so let's see the options. So let me again read the, one may conclude that the mapped contour of Nyquist contour in GSHS plane encircle the minus 1 point once in counterclockwise direction, right? Okay, so it is encircling the minus 1 point one time in counterclockwise direction. Okay, so the first option is correct. Second option, what it says, encircles the minus 1 point once in clockwise direction. This is wrong. Encircles the origin, no. Okay, because we are concerned about the minus 1 point. Okay, we are not concerned about the 1 plus GSHS. Okay, so any doubt in this case? Okay, so the question was asking NC. What is the value of NC? Because we already know the poles of open loop transfer function as well as closed loop transfer function. Okay, so NC is equal to Z minus P. Okay, so how to get the information for P? By looking at the open loop transfer function or the poles of open loop transfer function. Okay, so in this case you can see here only one pole, or the one pole is lying in the right half plane. So that's why P is equal to 1. And if you see the closed loop transfer function 1 plus GS HS equal to 0, so you can see all the poles are lying in the left half plane. So that's why the value of Z is equal to 0, and 0 minus NC is equal to 0 minus 1. So NC is equal to minus 1. That means minus sign indicates counterclockwise encirclement and 1 indicates one encirclement, right? Okay, so that's why the first option is correct. So any doubt in this case? Okay, let's go to the next question. In problem 1, let the transfer function be 2 by a square plus 7s minus 8. Considering unity negative feedback, one can infer that the controller structure is that of it. So this plant transfer function is this. Okay, so in question 1, what was given? If you go to the question 1, okay, so this is open loop transfer function was given. Okay, So let me again write this. This is PS. Okay. So GSHS. So it's a unity feedback. Okay. So HS will be equal to 1. So S plus 8. So this was the open loop transfer function. And this is the plant transfer function that's given in this question. And you have to find out what is the controller structure. Okay. So if you remember, let me draw the block diagram. Okay. So this is the controller block. Okay. For the negative feedback. Okay. This is how the block diagram looks like. Okay. So what we used to say, this is GS, right? So this is GS. So we have to find out what is CS. Okay. So you know HS is given in the question, that is equal to 1. Unity, negative unity feedback. That means HS is equal to 1. So GS is 2s plus 8 square plus 7s minus 8. Okay. And which is equal to C of S into P of S, right? GS is equal to CS into PS. Okay. So CS, you have to find out what is PS. So PS is given in here in the question, 2 into S square plus 7s minus 8. Okay. You just compare left hand side with right hand side. Okay. So what you can see, CS is equal to S plus 8, right? Correct. GS is given, PS is given, you have to find out CS. So CS is coming out to S plus 8. So what can you say about what type of controller this is? So we have S term and a constant term. Okay. So this term is like derivative term, right? Okay. And this is proportional term. Okay. So if you remember proportional derivative controller, how we used to write Kp plus Kd into S, right? Can you remember this form? Can you remember this? Okay. Just see, it's what is the coefficients here? If you just compare with this Kp plus Kd into S, so you can see here Kd is equal to, okay, just see the what is the coefficient for S? 1, right? And Kp is equal to 8, right? So this is proportional derivative controller. Okay, so what can we infer from the controller structure? It is proportional derivative controller, right? S plus 8. You can compare with the generic proportional derivative controller that you have studied when you are studying types of controllers. Any doubt in this question? We have to, very easy. We have to find out CS, and we got the CS as S plus 8, and we know it's a proportional derivative controller because it has constant term and a derivative term, right? So any doubt in this question? Okay, we'll go to the next question. So this is, let's consider a causal LTI system. Okay, causal LTI, that means we have a proper transfer function. So open loop transfer function has two low poles in the right half complex plane with the remaining poles in left half complex plane. Okay, so the information about open loop transfer function is given. So straight away we know P is equal to 2, right? Because it has two poles in right half complex plane. Okay, so from the plot of open loop transfer functions contour corresponding to the Nyquist contour, the corresponding negative feedback closed loop system will be stable only when. Okay, so we have to find out. So okay, you know this NC is equal to Z minus P. Okay, and what we have to find out is corresponding to the negative feedback closed loop system when the system will be stable. Okay, we have to assume we want our system to be stable. Okay, we want our system to be stable, and the question is asking what is the value of NC. Okay, because if you want your system to be stable, what should be the value of Z? Tell me. Already P is given. For the closed loop system to be stable, what should be the value of Z? Can you answer this? Okay, let me write what is P. P, you know, open loop poles lying in right half plane. Okay, what is right half plane? So this is S plane, right? Okay, so you're talking about this. Okay, this is right half plane. Okay, and for the stability of closed loop transfer function, what we want to do, we want to avoid the poles, okay, in this plane. Okay, so P is open loop poles lying in RHP, and what is Z? Closed loop poles. So it is number of, okay, this number of closed loop poles lying in right half plane. Okay, so what determines the stability of the closed loop system? Okay, so it depends on this Z, right? Number of closed loop poles lying in right half plane. For the stability, what we want is we want zero number of closed loop poles to lie in RHP. Okay, so what we want is Z to be equal to 0. If Z is equal to 0, that means closed loop system is stable. Okay, because there are no closed loop poles lying in RHP. Okay, so you see here, again we'll use the formula NZ equal to Z minus P. Okay, so P is given. Okay, so if you read this, open loop transfer function has two poles in right half complex plane. P is given, P is 2, and it's asking for the closed loop system to be stable. That means Z is equal to 0. Okay, how many encirclements are there around -1 point? Okay, so let's use the formula. Again, I am writing NC is equal to Z minus P. Okay, 0 minus P is 2. So NC is -2. That means there are, okay, two encirclement in because of the minus sign, we have anti-clockwise direction, okay, around -1 point, okay, in GSHS plane. Okay, this is what this NC equal to -2 means. Okay, two encirclement around -1 point, and minus sign indicates anti-clockwise encirclement. Okay, it's like this. Okay, let me roughly draw the GSHS plane. Okay, so this is -1 point, so the contour will be looking like this. Okay, let me see if it's right or not. Yes. Okay, and anti-clockwise. Okay, let me just draw it. This is rough. Okay, so it's similar to like this, two encirclement, that is anti-clockwise. Okay, let's see the option. So we have first one. If you see the option, the -1 point is encircled twice in clockwise direction. So this is wrong, right? The origin is encircled twice in clockwise direction. So we're not concerned about the encirclement around origin. Okay, so the -1 point is encircled twice in the counterclockwise direction. So this is correct. Last one. Okay. So any doubt in this case, NC equal to -2. So we are given with P, and for the stability we know Z should be equal to 0. So NC is equal to -P. So in this case, in our question, P is equal to 2. That's why NC is equal to -2. And what does this -2 means? There are two encirclements in anti-clockwise direction around -1 point in GSHS plane. Okay, so any doubt in this case? Okay, we'll go to the next question. Consider a negative feedback closed loop system whose open loop transfer function is given. So this is open loop transfer function. Okay. Okay. So here n is equal to 2 and m is equal to 1. Proper transfer function n is greater than m. Okay. Then one can conclude that the mapped contour of the modified Nyquist contour in GSHS plane. Okay, so now we have to find out the encirclement. Okay, you have to comment on same thing, Z minus P. Okay, let me again read the question. Consider a negative feedback closed loop system whose open loop transfer function is given. Then one can conclude that the mapped contour of modified Nyquist contour, okay, in GSHS plane encircle the -1 point once in clockwise direction. Okay, so you have to find out how many times it encircles the -1 point. Okay, so how to find out? So what can you say about the poles of open loop transfer function that are lying in the right half plane? Okay, let me go. This is so this is open loop transfer function. Okay, we also know what is the closed loop poles. How to find the closed loop pole? These are the closed loop pole, right? 1 plus GSHS equal to 0. Okay, so let me find out the closed loop poles also. So s square plus s plus 5 equal to 0. Okay, so if you solve this equation and find the roots, those roots are the closed loop poles. Okay, so they will be in the complex plane or the complex roots. So -1 plus minus p square is minus 4 to 5. Okay, so this one is this is 20 minus 1. So minus 19, right? 4 into 5 is 20 and 1 minus 20 is minus 19. So it's like j root of 19 by 2. And s2 is minus 1 minus j of 19 by 2. So if you see these roots where they're lying, so root of 19 is how much? Okay, don't have to worry because you know if you see this, okay, so the real part is always negative. So roots will be lying here, somewhere here. Okay, so because this point is, you know, it is equal to minus 1 by 2, right? And this point is plus j of root of 19 by 2, and this point is minus j of root of 19 by 2. Okay, so this is S-plane, right? So I am plotting the poles in S-plane. Okay, and you can see roots are lying in the left half plane. Okay, so what can we say about the system? System is stable, right? These are the closed loop poles, right? I'm plotting the closed loop poles and that are lying in the left half plane. Okay, so that's why this is stable. Okay, okay, so what can you say about this? NC equal to Z minus P. So Z is equal to 0, right? Z is again, I'm like discussing what is Z. Z is the closed loop poles lying in the right half plane. So in this case, you can see there are no poles that are lying in right half plane. Okay, that's why Z is equal to 0. And P, it's already you can see from the open loop transfer function is equal to how much? So P is equal to 0, right? So the two roots are lying in the on origin, but they're not lying on the right half plane or the right hand side of the S plane. So this is equal to 0. Okay. So there is no encirclement. Okay. So if you see this, it does not encircle the -1 point at all. Okay. So this is like the straightforward. Straightforward in the sense open loop transfer function is known to us. Okay. And we know the value of P also by looking at the open loop transfer function. Okay. And you can find the closed loop transfer function by 1 plus GSHS equal to 0. You can find the poles. Okay. So we found out the poles and we can confirm that the poles are lying on the left hand side of S plane. Okay, that's why Z is equal to 0 and P already we have seen was equal to 0. So that's why NC is equal to 0 minus 0 is 0. So there is no encirclement of minus 1 point in GSHS plane. Okay, so okay, but let's draw the Nyquist plot. Okay, and confirm. Okay, so this is given to me by looking at the open loop transfer function. Okay, we'll plot the Nyquist plot from minus infinity to infinity. Okay, so what we have to do in S plane, this region we are taking, right? So we have two poles here. This is the origin, right? And we have two poles at origin. So what we'll take this contour, right? Take this contour. This is of infinite radius. Okay. Okay. So let me just mark the points. This is J0 minus J0 plus. Okay. So this is how the S contour will look like. Okay, in the clockwise direction. Okay, so we have, you can see, let me break it down into pieces like, so you can see this portion. So we can draw the Nyquist plot for this from J0 plus to J infinity. Already we know from 0 to infinity, how can we draw the Nyquist plot? And correspondingly for J0 minus to minus J infinity will be the mirror image of that. Okay, so two more plots. So here this plot and the other plot is this plot, smaller plot. Okay, three plots we will combine and we will draw the GSHS plane. Okay, so let's first focus on Nyquist plot for 0 to infinity. Okay, so this is the open loop transfer function. So what is sinusoidal transfer function? So I'm just drawing the Nyquist plot. Okay, you can also write it down. Okay, from 0 to infinity. Okay, so what we used to do, what is the real part? Okay. So the real part is what? So j omega square, okay, it can be written like this, minus 5 omega square, okay, minus j omega by omega square is j by omega, correct? So the real part is minus 5 by omega square and the imaginary part is minus j by omega, okay? And if you find the magnitude, so what is the magnitude? 5 plus omega square, this is 5 square plus omega square by omega square, okay? So this is the magnitude and the angle is minus tan inverse omega by 5 minus 180 degree, right? Because if you see the denominator, you have j omega square, which right? Minus 180 degree. 90 minus 90 minus 90. That's why I combined together and written as minus 180 degree. Okay. So let's draw the for omega real part, imaginary part, and then we need the magnitude and the angle. Okay. For the omega equal to 0, what we can say about the real part 5 by 0 square, right? 5 by 0 is like what? Infinity, right? So it's like minus infinity. Real part will be minus infinity. And what will be the imaginary part? Similarly minus infinity. Okay, so I'm not writing J. So you can put in real part omega equal to 0, and in the imaginary you can put omega equal to 0. So you can see both are coming to be minus infinity. And what is the magnitude here? If you put omega equal to 0, okay, you'll get infinity, right? Summation of real plus imaginary, or directly in this you can put the omega equal to 0. What you will get is infinity. And what is the angle? Minus tan inverse of infinity by 5. Minus tan inverse of infinity, tan inverse of infinity is 90. Minus 90 minus 180 degree. So it's like minus 270. Okay, let me write this. This is minus 90 minus 180. This is minus 270 degree. This is for omega equal to 0. Let's put omega equal to infinity, very large value. So the real part will be equal to 0. And the imaginary part will also be equal to, and 0 plus 0, like, okay. So what you will get if you put infinity? 0. And the angle, what you will get is tan inverse of omega by 5. If you put omega equal to infinity, what you will get? Okay, I think so. In the first I did some mistake. Here in this case you will get 270. This minus 270. In the previous, when omega is equal to 0, you'll get minus 180. Okay, because tan inverse of 0 is what? 0 degree. So 0 degree minus 180 degrees minus 180 degree. Okay, this we got. So let's plot this. Okay, so you can see minus infinity, real and imaginary terms are both negative. So we can say it's in third quadrant, right? Somewhere here. Okay, and at infinity, what it's the magnitude is going 0. So it's like something like this. Maybe I'm drawing wrong. Or minus 270 degree. Okay. Okay, this is 270 degree. Okay, so I did. So you can see here I did some mistake. Okay, let me correct this. So if you see this angle, okay, so here it's minus tan inverse, not minus, plus. Okay, so this was the mistake, because you can see this term. So I'm finding the angle for this. So numerator is plus tan inverse omega by 5 minus 90 degree minus 90 degree, 290 degrees, so that is minus 180 degree. Okay, so sorry for this. So this is plus. So what you'll get, minus 90. Okay, so that's why you'll get something like this. Okay, okay, plus infinity, let me write. Okay, so if you try to construct for the minus infinity to 0, so what you'll get, so just put, you can put like minus infinity in the real and imaginary. Okay, let me not do this. Let me again make the same thing, and we'll also plot for the, so this is magnitude. Okay, so because 0 minus and first is and in minus infinity. Okay, if you put 0 minus, the things will be same, right? Same, you'll get minus infinity, you'll get infinity, and if you see the angles also, you'll get minus 180 degree, very small quantity. Okay, but if you put minus 180 degree, okay, so what is real value will be, okay, something is different. Okay, if you see omega equal to 0 minus, real part will be infinity. Okay, so real part, if you see this omega square, right, very negative value you're putting, less than like point minus 0.00 something. Okay, so this will be minus infinity. Okay, so let's also see for the imaginary. If you put omega to be very small value, it's close to 0, but minus 0.00, minus minus cancels. So what you will get imaginary part to be some positive infinity, right? So this was wrong. So you'll get some positive value here. Okay. So real part is still negative because it's omega square in the denominator. Okay. But for the imaginary part, you can see what you will get, omega by minus omega square. Okay, so that's why omega is some negative value, that's why you're getting some positive value. Okay, and for the infinity, what you will get, real part is equal to 0 and imaginary part will be also equal to 0. Okay, so if you see angle will be, let me again for the imaginary part, so minus infinity. Okay, so if you put minus infinity here, so some positive value you will get. Okay, so this is also minus same 90 degree. I think one difference is this one. Okay, let me plot this. So at infinity, minus infinity, you'll get 0, 0, minus 90. Okay, I think you should get something else. So here you'll get, okay, so you are putting tan inverse of minus infinity okay, minus 180 degree. Okay, so what you'll get, this will be minus 90 minus 180 degree. So it will be minus 270 degree. Okay, so minus 270 degree is this. Okay, so it will start from minus 270 degree, and if you see what is the at 0, it will go to, it is going here. Okay, this is, so let me, this is, okay, I should get real part to be negative. Okay, I think I'm stuck on this. I'll just get back to this question at the last. Okay, let me do the rest of the questions. Okay, so let GSHS be the open loop transfer function of the negative feedback closed loop system. Then the closeness of the GSHS locus to the -1 point is indicative of this. We know it's a relative stability, right? That's a definition. Okay, so consider a unity negative feedback closed loop system whose open loop transfer function is given. Then the gain crossover frequency is, so you have to find the gain crossover frequency. So what is the magnitude? So directly I'm writing it. Okay, so if you put here j omega, let me not skip that step. Okay, okay, it will be minus omega square plus j 2 omega. Okay, because minus j omega square is minus omega square, j square is equal to -1. Okay, so here this will be the magnitude. Okay, this is the magnitude, and we have to find out the gain crossover frequency. So you know the gain crossover frequency, the magnitude is equal to 1. Okay, so let's put the magnitude equal to 1. Okay, so squaring on both the sides, what you'll get. So this is -1 equal to 0. Can we not write omega g whole square to be, okay? Let me call this as some omega c. Okay, so this is omega c square plus 4 omega c minus 1 equal to 0. Okay, the substitution we have done, and omega c is positive, right? Because it's omega g square, and omega g also, you know, it's a frequency, so positive value. Okay, so let's solve this. So omega c is minus 4 plus minus 16, that's 4 square minus 4 into 1 into minus 1. Okay, minus 4 AC. C is minus 1. Okay, 2. So this is minus 4 plus minus. This is 16 plus 4 is 20, right? So we'll not take the negative value. Okay, because you know omega c is positive. So omega c is minus 4 plus root of 20 by 2. So we have discarded the omega minus omega c value which was negative because you know this. Okay, and to find out what is the value of omega c now. Okay, let's find out. So this is 2. I'm getting 0.236. Okay, but you know you have to find omega g, right? Omega g is root of this. Let me write the relation first. Okay, and omega g is only positive root. Okay, because we know omega g is also positive. So I'm getting 0.4857. 58 I will write, or okay. So this is in radian per second. Okay, so answer is 0.486. So it's very simple question. Okay, you have to find out the magnitude of sinusoidal transfer function, open loop transfer function, and equate it to be equal to 1 at a frequency. Okay, so we have to find the frequency. So at omega g equal to 0.4858, you'll get the magnitude to be equal to 1. I hope there shouldn't be any doubt. Okay, it's very simple question. Next is this, the phase crossover frequency. Okay, we have to find out the phase crossover frequency. This is the frequency at which the phase becomes minus 180 degree. Okay, so what is the phase? First again write out the open loop transfer function, which is 1 by s square plus 2s. Okay, so we know if we write s equal to j omega, what you'll get is okay, and if you try to find out the phase, it will be minus tan inverse of 2 omegas by minus omega square. Okay, which will be equal to plus tan inverse of 2 by omega. Okay, so this is the angle. So what is the phase crossover frequency? It is the frequency at which this angle becomes minus 180 degree. So at phase crossover frequency at omega p, this phase becomes minus 180 degree. Okay. I hope doing everything correct. Square plus 2s. Okay, so what is, let's do in this way. So what is tan inverse of minus 180 degree? So what is like minus tan inverse of 180 degree? Okay, this will be equal to 0, I think. Tan inverse of 180 degree is 0, 0, 180 degree. Okay, so when can this 2 by omega p uh, can become 0? When omega p is tending to infinity, okay, then we can say, because this is 0, right? When omega p is tending to infinity, 2 by omega p will be tending to 0. Okay, so that's why omega p is equal to infinity. So the phase crossover frequency is infinity, right? So what you could have done simply, so I could have done like this also, 1 by s into s plus 2. Okay, then if you take the, let me make space, if you calculate the angle, it will be easy, very straightforward. Okay, so if I calculate the angle for this, so what is the angle you'll get? If you, okay, let me again do one more step. J omega and j omega plus 2. So it will be minus 90, okay, minus tan inverse of omega by 2. Then it's very easy. At omega p, okay, so this is equal to 180 degree at omega p, right? So tan inverse omega p by 2. So if you take the minus 90 degree to that side, it will become minus 90. So tan inverse of omega p by 2. Okay. So when omega p is infinity, then tan inverse of infinity is equal to 90. Okay. So this is one way. So this is simpler, like tan inverse of infinity is equal to 90. Here also you can do tan inverse of minus 180 degree is 0, and 2 by omega p, how it can become 0 when omega p is infinity. Okay, so phase crossover frequency is infinity. Okay, any doubt on this question? So two ways, like, okay, both the ways it will lead to the same answer, omega p equal to infinity. Okay, in problem 8, the phase margin is, so in problem 8 the open loop transfer function is same. This S2 is plus 2. Let me write this way. Phase margin is plus 180 degree plus the phase of the open loop transfer function at gain crossover frequency. Okay, so this is the definition of phase margin. So in this case you have to take phase at gain crossover frequency. Okay, first, what is the phase? Let me find the phase. It is equal to minus 90 degree minus tan inverse of omega by 2. Okay, the previous question itself we have found out this one. So this is the, again in the next question I'm writing minus 90 minus tan inverse of 2. Okay. So at omega g, we have to find out what is the phase. So at gain crossover frequency. So what is the phase? So gain, omega g is what? In 8th question we have found out. It's 0.48. So according to the question, it is 0.486 radian per second. Okay. So let's find out minus 90 degree minus tan inverse of 0.486 by 2. So what is this tan inverse of 0.486 by 2? So it's 13.65. Okay, 66. Let me write this 66. So this is the phase. So let me find the phase margin. Phase margin is 180 degree plus this, which is minus 90 minus 13.66 degree. Okay. So it will be 180 degree minus 90 minus 13.66. So 90 minus 13.66 degree. Okay. It's 76.34 degree positive, right? So this is the phase margin at gain crossover frequency. 76.34 is the correct answer. Okay, so you should know what is the definition of phase margin, which is equal to 180 degree plus the angle. Okay, so we have to calculate the phase at gain crossover frequency. So what we know about the transfer function, this is the gain, this is the phase at any omega. Okay, so if you put the value of omega g in this phase, you will get the phase at gain crossover frequency, which is coming out to be minus 90 minus 13.66, like 103.66 will be the phase, and phase margin is again 180 degree plus the phase at gain crossover frequency. So we are getting phase margin as 76.34. Okay, so any doubt in this question? Okay, let me go to the question 11, which is in problem 8, the gain margin. Take two. So gain margin is what? So this is at phase crossover frequency, right? So this is the, or you can say minus 20 log of, okay. So this is the definition. So this one is in dB, one is in absolute term. So let's first find out the what is the magnitude at phase crossover frequency. So what is the magnitude first? So magnitude is equal to, so before that, let me write the open loop transfer function, which is Okay, so it's if you put s equal to j omega, okay, so what is the magnitude? Magnitude will be 1 by omega into root of omega square plus 2 you'll get. Okay, so this is the magnitude, and you have to find out the magnitude at, let's find out the magnitude when omega tend to, because see what we have calculated from the previous questions. You see, the phase crossover frequency is infinity. You have to find the magnitude at this point. So what we can see, okay, so you can find like this: omega is omega p, yeah, or limit omega p, you know, tends to infinity, and this is omega p root of omega p square plus 2. Both the things are same, right? So what we can see, what is gain margin in this case here? As omega p tends to infinity, okay, what is this magnitude? So if you put the limit, you'll get 0, right? Because omega p is infinity and it's in denominator, so you'll get 0. And what is gain margin? It's reciprocal of this. So what you'll get? Infinity. Okay. So we have calculated the magnitude, and we know omega, if you put omega equal to omega p, then we are calculating the magnitude at omega p. Okay, so you can put the limit, right? So if you put the limit, you will get, because omega p is tending to infinity, so your magnitude will be 0. Okay, so gain margin is 1. It's a reciprocal of the magnitude. So if magnitude is 0, then that means your reciprocal is equal to infinity or tending to infinity. So that's why the gain margin is tending to infinity. So infinite gain margin. So any doubt in this case? So step by step, we are calculating, we have calculated the gain margin. Okay. First we calculate the what you say, magnitude, okay, of the open loop transfer function or sinusoidal transfer function. Then when omega is equal to omega p, what is the magnitude? In this case, it's 0, and reciprocal of that is equal to infinity. Okay. So the closed loop poles corresponding to open loop transfer function given in problem 8 are, okay, it's very simple, like, okay, these questions are done many times. Okay, so 1 by s into s plus 2. So this is the open loop transfer function. Okay, so it's asked to find the closed loop poles. So you know closed loop poles. Okay, so closed loop transfer function, it is gs by 1 plus gs hs. Okay, and you know to find a closed loop poles, you have to write the characteristic equation and equate it to 0. And the roots of this is the closed loop poles. Okay. So what you'll get if you can write this form. So both the roots are same in this case. Okay. So you're getting multiple roots at s equal to -1. Okay. So second one, this is correct. Okay. So you're getting two roots and both are at -1. So multiplicity in this case is 2. Okay. At s equal to -1. Both roots are same. Okay. I hope there is no doubt in this case. Okay, 13th question. Consider the closed loop sinusoidal transfer function corresponding to problem 8, the low frequency value of its magnitude. Okay, so in this case, if you see the question, it's asked about the closed loop sinusoidal transfer function. Okay, so in this, so if you go back to 8, so it's very important you read this unity negative feedback. Okay, so that means HS is equal to 1. Okay, because here we have to write the closed loop transfer function, which is GS by 1 plus GS HS. Again, let me write HS is equal to 1. Okay, so if you write this, what you'll get? Okay, so you're getting this closed loop transfer function, which is y of s by r of s. Okay, this now you have to find the sinusoidal transfer function. You put s equal to j omega. Okay, or you can write what s plus 1 equal to square, because already in the previous question we have found out the closed loop poles. Okay, and let me call this as closed loop transfer functions C of s. So C of s is this. Okay, and the sinusoidal transfer function is when you put s equal to j omega. Okay, and low frequency magnitude in dB. Okay, so let's find the magnitude here. Magnitude is equal to, it will be omega square plus 1. Okay, okay, I will do the steps. So this is square, right? So you'll get, so you can write like this. Okay, so in the question it's asked low frequency asymptote value in magnitude plot, right? Okay, so what you can see now, low frequency asymptote means when omega is very small. Okay, it's close to 0. So if you see the magnitude 1 by omega square plus 1. So if you compare omega square plus 1, like omega is very small, 0.00 something, 0.001. And if you square it, the value, the absolute value becomes even smaller than the omega. So omega is very, very small. So you can neglect with respect to 1. Okay, so that's why. So let me write here. And omega is tending to 0. Okay, so this will be equal to 1. Okay, because omega is 0. So in dB, what we can find out, let's find out in dB. In dB, it's 20 log of base 10. This. Okay, so what you'll get is, if you put omega equal to 0, this is equal to 1, right? At that point. So you'll get 20 log of 1, which is equal to 0. Okay, you're getting it? Why it is 0? Okay, because if you try to plot the okay, let me plot the Bode plot for this function, because this is the closed loop transfer function. So what you'll get is, this is the magnitude plot I'm drawing. Okay, this is 1. Okay, this is omega. So you'll get 0 dB, and then this. So this is 0 dB, and the slope here is minus 40 dB per decade. Okay, so what we have seen, how to calculate the slope at the for the high frequency region is minus 20 n minus m dB per decade. Okay, so this was the formula, right, for high frequency asymptote. Okay, if you know n here is equal to 2 and m is equal to 0, so that's why if you use this, you'll get minus 20 into 2, that's minus 40 dB per decade. And in this particular question, we are asked this. Okay, I hope everything is clear. This is I'm drawing the Bode plot, magnitude Bode plot for closed loop transfer function. Okay, so we are given with open loop transfer function, and we have found out the closed loop transfer function, and from the closed loop transfer function to closed loop sinusoidal transfer function by putting s equal to j omega. Okay, and this is finding the magnitude, and the magnitude is 1 by omega square plus 1. Okay, and if you put omega equal to 0 or omega is very, very small, you'll get the magnitude to be equal to 1. And if you take the magnitude in dB, you'll get 0 dB. Okay, and this is how also I have drawn the Bode plot for the closed loop transfer function. I hope there is no doubt in this question. Okay. So 14, corresponding to problem 8, the slope of the high frequency asymptote of the closed loop sinusoidal transfer function. So in D, it's asking in dB per octave. Okay. So in the previous question itself, I have discussed the slope in dB per decade. Okay, let me copy this. Okay. So this is in dB. So if you want to calculate in octave, on octave, you will get this. So it's plus 6 per octave. Okay, so n is equal to 2, m is equal to 1, and I'm just writing it here, you'll get minus 12 dB per octave. Okay, because you have two poles, that's why you're getting minus 12 dB per octave. Okay, so corresponding to problem 8, the cutoff frequency of the closed loop sinusoidal transfer function. Okay, so what is the how do we calculate the cutoff frequency? So we take the, okay, let me again copy this. Okay, so cutoff frequency is this frequency. Okay, so at this point is minus 3 dB. Okay, and we have to find the omega c. Okay, let's find out. So problem 8. Okay, sorry, this is not the problem 8. Let me, this is for the previous problem. So delete. So for problem 8, problem A, we have open loop transfer function. Okay, and let me go stepwise. Okay, and for that, what is the closed loop transfer function? Okay, closed loop transfer function, first is open loop transfer function, second we derive closed loop transfer function, and third step is plot the Bode plot of closed loop transfer function to find the cutoff frequency. Okay, so let me draw the same graph. This is 0 dB. Okay, C of j omega, magnitude in dB, and this is omega, and we have to find out this. This minus 3 dB. Okay, and what is the magnitude? In the previous question we have found out this 1 by, so this is, I will just highlight this. This is the closed loop sinusoidal magnitude. Let's copy this. Okay, so let's find in dB. Okay, because in dB, what you do to find 20 log of Cj omega, which is, okay, so this will be equal to minus of 20 log omega square plus 1. Okay, I hope everything I'm doing is correct. Let me find out correct or not. Correct. Okay, so you And okay, this is the magnitude in dB. Okay, at cutoff frequency, this magnitude is equal to minus 3 dB, right? So I'm just equating in dBs, magnitude in dBs. So you will get omega square plus 1 3 by 20. And what you can do, if you remove the log, then it has to be 3 by 20. So what is 10 raised to power 3 by 20? It's coming out to be 1.4125. Okay, so this is, so okay, omega c, let me write the subscript here. So omega c square is equal to minus 1. So it's 0.4125. So let me take the square root, then I'll get the cutoff frequency. So I'm getting cutoff frequency to be 6424 radian or 6425 radian per second. Okay. So option first is correct. Okay. So this is okay. So this is in radian per second. So this is the cutoff frequency. Okay. So any doubt in this case? So we are given with open loop transfer function, then we have the closed loop transfer function, and then we are plotting the Bode plot for closed loop transfer function. Okay. So it's just looking like this, and at low frequency asymptote the magnitude is equal to 0 dB, so that's why minus 3 dB. Okay, so we have got this 0.6425. Okay, so any doubt in today's session? I have to do one more question. Okay, for the uncompleted question. So let me take a look. Okay, so here we are calculating the Bode plot. Okay, for the negative or for the positive frequencies, I got the correct Bode plot. Okay, and for the negative frequencies, I was struggling. Okay, let me see. At omega 0 minus, I was getting infinity. Okay, if I put omega 0 minus, imaginary will be positive, but the real part will be negative. Correct. So this step is correct. Second is minus infinity. If I put real part is equal to minus 0. Correct. And the imaginary part is minus infinity, it will be positive. Okay, fine. Okay, so it's if you calculate the angle, you're getting minus 180 degree. Fine. At omega equal to 0, at minus infinity you will get minus 270. Okay, so this point is for the negative frequency minus infinity, and this point is omega tending to 0 minus. Okay, this we have finished. So we have to complete this, right? So let's look at the contour. This is the closed contour. So I have plotted for two regions for the yellow portion and for the green portion. Okay, so green portion, what is this? How I will get? So let me write in green. S is infinity, so GSHS, or you can also put omega tending to infinity and g of j omega h j omega. Okay, let me because it's a proper transfer function, you will get 0. So this is what is GSHS. S plus 5 is a square. Okay. Okay. So what you will get here if you put s equal to infinity, obviously you will get 0, right? Because it's a proper transfer function. HS is proper transfer function. So you should get a 0 or a non-zero positive value. But here we are getting 0. Okay. So what is that point? That point is, let me put 0, this point. Okay. So whatever I have calculated with the green color corresponds to 0 or origin point. Okay. So I'll write it here. Infinite semicircle radius contour is mapped to 0 in GSHS plane. Okay, so it's single point 0. So this infinite radius, this is mapped to a single point 0. Okay, now we have to worry about the pink highlighted portion. Okay, so what is that pink highlighted portion? So here S, we have taken very small value, right? E j of theta here. So let me just show you the zoomed version of that. Okay, so it is like this. So we have two poles at origin. Okay, and we have taken a small semicircle like this. Okay, where it's very small, from 0 minus to 0 plus. Okay, so okay, and this is from minus 90 to 90. Okay, so we are going anti-clockwise type. Okay, so theta is from minus 90 to 90. Okay, so let's put this in GSHS. So let's find out what is. So if you put this, what you'll get, plus 5 you'll get, correct? And in denominator you have square. Okay, and from the numerator, what you can see is this is very small. Okay, this quantity is very small as compared to 5. Okay, you can neglect that. Okay, so what you'll get is 5 by theta square and j e 2 theta. Or let me do one more step, minus j 2 theta. So 5 by theta square is very large value because theta is very small. So it will tend to infinity. Okay, it will tend to infinity. And if you see how the contour is looking like, if we are going from anti-clockwise direction minus 90 to 90, what will be the theta in this case? So you'll get minus of 90, 2 into 90, you'll get plus 180 degree to minus 180 degree. Okay, so you went from, this is clockwise, so you need to focus on this one. So let me highlight this. You went, okay, let me write it. This is clockwise. Okay, so clockwise is minus 90 to 90. So we have seen from the contour also. Okay, how we are going? You have taken anti-clockwise, right? Overall direction is clockwise, so this is clockwise, that is the definition. But if you see the small semicircle, you have taken clockwise. Okay, so but again, if you see this, what you will get? If you put minus 90 here, you'll get plus 80 to minus 180, that is clockwise. Okay, negative of that angle. If you're going anti-clockwise, so here you'll get, so this is anti-clockwise. So this is clockwise, okay? So plus 180 to minus 180 degree. Okay, if you go from 0 minus to 0 plus, so you have to go from plus 180 degree to minus 180 degree. So if I complete this, okay, so I'll get something like this. You have to, if you want to get the proper graph, you want to plot in the MATLAB, something like this. Okay, so it's like infinite graph. We just, radius is infinite, but from 0 minus to 0 plus. Okay, from plus 180 to minus 180, and it should be in clockwise direction. So clockwise is this. Okay, so it's, if you see it, it completes like, just follow the direction like this. Okay, so this is, you can see just matching, right? So you can see the point minus 1 is here, somewhere here. So minus 1 point is somewhere here. So you can see they are not encircling this point. Okay, so this is G of H, GHS plane, and this is the Nyquist plot for the transfer function. So you can see, so minus 1 point is not encircled for this case, and that's why we didn't have the, we can say it's a, does not encircle the minus 1 point, and Z is equal to 0 because PE was equal to 0. Okay, by from the Nyquist plot, also from the Nyquist plot of the GSHS. Okay, so any doubt for today's session? Okay, few questions were very simple. Initial, you have to find the open loop poles, closed loop zeros. Okay, but they are for the purpose, because we also have to build on this concept of Nyquist stability. Okay, NC equal to Z minus P. Okay, so in today's question, in today's assignments, I have discussed few things. Okay, just you try to for the question 6, you try to make the Nyquist plot. Okay, using MATLAB or some software, or using hand also you can do. Okay, and try to find out exactly how it looks. Okay, it is similar to this or something else you're getting. Okay, and I think other questions are simple: gain margin, phase margin, gain crossover frequency, phase crossover frequency. Okay, simple things. Okay, If you have any doubt, otherwise I'll close the session.
Thank you, sir.
Okay. Okay. Thank you for attending the session. So I'll meet you in the next session on Tuesday. Thank you.